Now we are using Biot-Savart's law to calculate the magnetic field from a straight wire. Okay, so we consider a system of a straight wire with the current I flowing through the right hand side by the right arrows. Yeah. So we are trying to find the magnetic field at this point P. Okay, so B is equals to what at this point? Okay, and then the important part of considering the Biot-Savart's law is to define the dl and to define the r. So dl will be the small elements of the charge at a point that I try to divide and the length L into the small length dx. Okay, and then we define the vector dl that has the length of dx and has the direction to the right hand side in this picture. Okay, and for r here is the direction. So the direction is determined from the source. Or let's say the source is the current at the infinitesimal length of dx. And then the direction is going towards the point P. So direction towards the source to P, okay, in this picture, it will be this vector in the orange color. Okay, so dl, which has the length of dx, and cross product with the unit vector r. And these two vector is making the angle of phi. So dl cross r, okay, will be dx as the magnitude of unit vector r is 1. So it will be dx times by 1 and times by sine phi. Okay, and the direction will be outward using the right hand rule. Okay, and from this picture, we can then write down the dx psi phi as dx cosine theta as we try to see the relationship between the angle phi and the angle theta. Okay, so this is from your trigonometric class, dx cosine theta. Okay, and it is in the outward direction. So that we substitute these expressions into the Biot-Savart's law, and we will be given B. Okay, so this time I will just consider the magnitude of B as mu 0 over 4 pi, in which mu 0 is the permeability. Okay, and times by integrate I and times by dx cosine theta and divided by r square. Okay, and then from this I will just consider the right triangle that is made by r, which is the distance from the closest distance from the wire to P, and then is made by x and r. And the distance r here, it will be the square root of x squared plus r squared. Okay, so that cosine theta, cos theta, from this picture, it will be the big R divided by the small r, or the square root of x squared plus r squared. Okay, so I substitute this expression for cosine theta into our integral, and we have mu 0 I. So the current I is constant, so I pulled it out from the integral over 4 pi, and then for cosine theta as r over square root x squared plus r squared. R is also a constant, so I also pull this out from the integral. And what I have left in our integral will be the integrate of dx. I would say from x1 to x2, and then divided by the square root of x squared plus r squared, and power by 3/2. Okay, because cosine over here is actually x over is actually r, big R over small r. So the one small r here and two small r here will make the small r of the power 3, and it will become the x squared plus r squared and power by the 3/2. Okay. And then we are going to perform this integral. Okay, so from this integral, I have already proved. Okay, you can see from this proof that this integral of 1 over x squared plus r squared to the 3/2, you would have this, okay, for the answer, in which we are going to give you the formula in the exam. Okay, so that we have the constant mu o I r over 4 pi, and then we have the x over r squared times by square root of x squared plus r squared, and taking the upper and lower limit from x1 to x2. Okay, so now we have the magnetic field, and that is pointing outward. Okay, so from this formula, it would just be depend on the limit. Okay, so we are going to take the different lower and upper limit. For example, for the case 1, so if I have the easiest case that if my current line is infinitely long, okay, and I want to find the magnetic field at point P, okay, and this point P is at the distance r from the current. Okay, so what I do is I will take the limit x1 as minus infinity and x2 as infinity. Okay, so that B, or the magnitude of magnetic field, it will be the constant mu 0 I r over 4 pi, and taking the upper limit, so it would be x over r squared, and this square root here will become x. Okay, because if as x approaching minus infinity, you're gonna have x squared plus r squared, square root x plus r squared, approaching x, because x is much bigger than r, so you can take r out. Okay, and then for the lower limit of limit of x1 with minus infinity, sorry, the last case was infinity. So if for the minus infinity, I can say that this is the minus x and divided by r squared and x. Okay, so using the same approach, you having the square root x squared plus r squared as x. Okay, and then I'll just cancel all the x out. Okay, so that's in your in your parenthesis term, I'm going to have, okay, so I'm going to have this constant, then times this by 2, because this is 1 and then minus 1, so you have 2, and then divided by r squared. Okay, so this is what you have for the infinite y. Okay, so I just cancelled r, and you are going to have b as mu over 4 pi I and times by 2 over r, or some might say that it is mu 0 I over 2 pi r. Okay, and for the case number 2, okay, so if I want to have, like for example, the y that start from here and then extend to infinity, okay, and I want to find the magnetic field here. Okay, then I'll just take the upper and lower limit. So I'll just take the upper limit as x1 equal to 0 and x2 approaching infinity. Okay, so now my b will become the constant mu 0 IR over 4 pi, and then I will take the upper limit. Okay, so maybe I'll just get our expression from here. Okay, so if I do x2 infinity, okay, what I have for this term is, it will be, okay, let's say I will just write infinity something here, and divided by r squared, and then divided by infinity. Okay, so that x towards infinity will be cancelled out in this term. Okay, and then if I substitute 0 in the other term, it would be 0 divided by r squared and over the square root of something, which should give us 0. Okay, so that what left for you is just 1 over r squared over here. So that b will be equals to mu 0 IR over 4 pi r squared, and I cancel one of the r, it would be mu 0 I over 4 pi r. Okay, so so it would be half of the answer that you get from you having the current from minus infinity to infinity, but this time you have just only the half of it. So your magnitude of the magnetic field will be half. Okay, but if you have like the finite size, for example, if my current line is limit from just like minus L to L, okay, and you want to find the magnetic field over here, I'll just take substituting the x1 as minus L and x2 as L, and using the same formula here, I'll just use B as mu 0 IR over 4 pi, okay, and I substitute the L inside. So that would give you L over r squared times by the square root of L squared over r squared. and minus by the minus L over R square times by the square root of L square plus R square. Okay, so this would give you B of mu 0 I R and times by 2L, and on the denominator you have 4 pi R square and times by square root of L square plus R square. Okay, and I will cancel some of the term. I can cancel one of the R, I can cancel 2, so you have 2 down here. So finally you just get B as mu 0 I and over 2 pi. Okay, and then let's times by L. Sorry, I also have R here, and times by L over L square plus R square, square root. Okay, and and from this, if you take the limit of L approaching infinity of B, okay, you're just gonna get back the mu 0 I over 2 pi R, and here you just have L over L, because if L approaching infinity, L square plus R square, square root of L square plus R square will be just L. Okay, and you can cancel L with L, and you are going to have mu 0 I over 2 pi R. So it's similar answer to what you have at the case 1. Okay, so that is the idea for using Biot-Savart's law with straight lines.